All right. Last class period, we talked about electric generators. And God's my witness, I couldn't find my cool demonstration for... Oh, wait, here it is. Found it. Today, we're going to talk about eddy currents and inductance. And so this picture I have up here is a thing that is often called a mutual inductor. We'll learn about it, but a lot of people know this by a different name. It's a transformer. It's a robot in disguise, right? So we're going to learn about transformers, among other things, today as well. So let's get started with some questions reviewing what we learned in class last week. So what will not produce a magnetic field? Will change in the magnetic flux through a stationary coil produce a magnetic field? So this one will. Yes, it will. Yes, it will. Will through a constant magnetic field produce a magnetic field?
Yeah.
Oh, wait, no. The coil one will. The wire one won't. It's a trap.
Okay, anyway. Moving a wire through a constant magnetic field. Initially, it will cause a surge in current. But then it will reach equilibrium. There'll be no current, hence there'll be no magnetic field. So this one would be a no. And moving a coil through a constant magnetic field. If I move the coil through a constant magnetic field, is it going to make a current in it? You have to have a changing magnetic flux. So that's a no as well. So which will not produce? These two. Which one will produce? The top one. All right, Lenz's Law. Remember we talked about Lenz's Law, and I said that minus sign in Faraday's Law of Induction reminds me I need to apply Lenz's Law. So let's once again go through each statement. A changing magnetic flux induces an EMF. Is that a true statement or a false statement? It's a true statement. Is it Lenz's Law? No. What is it? It's true. It's Faraday's Law of induction, but Faraday's Law. A changing current induces a magnetic field. It's true. Let's go to the next one. A current creates a magnetic field. This one here is true. This is Ampere's law. And since a current creates a magnetic field, if that current's changing, it's just going to create a changing magnetic field. So the one above it is also okay because it's just going to produce a changing magnetic field. So those are both okay, but they're not Lenz's Law yet. The next one, a changing current induces an electric field.
Yeah, because isn't that what opposes the changes of the magnetic field?
Well, we will learn Maxwell's laws soon. By the way, for the test, I am not going to put chapter 24 in the test because I want you to have time to cover stuff. So it'll only be over chapters 22 and 23, which this is still 23. And I did make a worksheet for chapter 22 last night, which I will post after class today. Only posting after class today because I haven't had time yet to post it. Mira.
I mean, for the next test, it'll be all of optics and chapter 24.
Well, chapter 24 fits with both topics.
Okay.
Optics is electromagnetic waves. Chapter 24 is transitioning from magnetism and electric to electromagnetic waves. So it goes either way. So it's not really breaking things up except for it's making one test is only over 2 chapters and one test it's over like 4 chapters or something like that. Lydia.
2 questions. Does that change what we need to be doing on open stats for our reading quizzes?
I don't think so. I made an adjustment by one day, and I think I have it covered. I probably should go back and look again.
And then for the scrapbook, do you still want us to cover 24 then?
You know what? No, let's just.
Do just 22 and 23?
Yeah. I mean, well, if you have 24, right, if you have 5 and 24 is one of those 5 or 2 of those 5, it'll be okay. But if you just have 22 and 23, that's okay as well.
But still the 5.
Yeah, it's still 5. Yeah. Good questions, though. It's good to be clear on what's expected, not, I don't know, thought I did the right thing. Okay, so a change in current induces an electric field. We will learn that actually is fundamental to what's going on with electromagnetic waves. But that was also not Lenz's law. So Lenz's law must be an induced EMF acts to oppose the change in magnetic flux. So if the magnetic flux is getting stronger, then the induced EMF is going to try to weaken the magnetic flux, or the induced, current is going to try to weaken it, and vice versa. Now, a review of everything we've learned in electromagnetism. We have, right, this is good since we have a test coming up a week from tomorrow. We had electric force, where we learned that like forces repel and opposite forces like charges repel and opposite charges attract. We had 2 types of charge. So first semester, all we had was gravitational force with 1 type of charge, mass, monopolar. With electric charge, we had 2 types of charge, positive and negative. And then we have the rule on what happens if they're the same, if they're the opposite. So we had Coulomb's law to tell us about that force. We have electric fields as a way of making it easier for us to calculate what the force is going to be on any old charge I bring into a certain environment. We calculate the electric field due to the charges in this environment. If I bring another one in, I just take this charge, multiply by the electric field vector, and it gives me the force. That's the point of the electric field. Now, we have gone beyond that in usage of the electric field, but that was the point. Then we got to magnetism. Magnetism also has 2 types of charges. Instead of calling them plus and minus, now we call them north and south. We could call them plus and minus, it would work. But we call them north and south instead. North for north seeking. That is, if you let a magnet freely rotate, it's going to point toward the Earth's north geographic pole. Furthermore, we learned that when you have a magnet in a magnetic field, it will create a torque to try to make the magnet align with the field, so that the magnetic field lines come out of the north and go into the south. Which brings you to then the clumsy, awkward conclusion: if the north-seeking pole has magnetic field lines going out of it, and then they're going into the Earth's north geographic pole, magnetic field lines go into which pole of the magnet? South. So the Earth's north geographic pole actually is a south magnetic pole because of our definition of what a north magnetic pole is. So why do we have magnetic field lines? So we can calculate the force. Now, everything that we have done has simply been calculating the force on a charge due to a magnetic field, or a current, since a current is a collection of charges, due to a magnetic field. Obviously, there are ways of calculating the torque created between 2 magnets, or the force between 2 magnets, but that is beyond the scope of this class. So make sure that you can remember those force laws, your right-hand rules, and how they apply. Using those force laws, we were able to do things like understand how an electric motor works. We had 2 right-hand rules in the electric motor. One because torque is equal to R cross F, and one because force is equal to IL cross B. Moving charges create a magnetic field. For people in physics, 152, Ampere's law is the only one you stayed on this. People in 252, we also stayed the Biot-Savart law, which is kind of like the Coulomb's law version for the magnetic field created by moving charge. And then the final thing we've learned is about induction, Faraday's law of induction and Lenz's law to give us the direction. So that's a review of what we've learned. Now we're going to apply that to some odd situations. And the first one is what we call eddy currents. And I like to start this with no discussion except for an experiment. So here I have a copper tube. Copper is a metal, it's a conductor, but it's not magnetic. Here I have two things that look the same. They are not attracted to the copper here. One of them, okay, that's got to find something. One of them is magnetic, one is not. What kind of magnetism are we seeing here? Ferromagnetism. Ferromagnetism is the strong type that will attract. If you put something that's ferromagnetic in a magnetic field, it will be attracted. So, I'm going to take this, and I need somebody to help me. Somebody. Okay, Mira, you raise your hand first. So, Mira's job, it can be one of two things. Hold this vertically, or drop one of these through the center of it. Which one do you want? Okay, so hold it by the top and kind of let it hang to keep it as vertical as possible. Now, I'm of course going to try to figure out which one's which again. So this one here is the one that's not a magnet. Now I'm going to drop it down here, and first of all, I have to specify if I hit on the sides, it will sit there and roll on the sides and come down slowly. You'll hear it. If that happens, we'll just have to do it again because I didn't drop it well. Understand? See, you heard it. Cancel it. Okay, make sure it does drop, hang vertically. That's it. Better, but still was hitting the sides. That's the best I'm going to do. It's hard to do. When I was at PUC, I had some bigger pipes, much easier. Also, had 2 stories with the drop it down, which was totally cool until my student hit his head on a speaker. Okay, now the magnet, doing the same thing.
What did you say?
I dropped the magnet through here. The magnet went really slowly, whereas the non-magnet one went quickly. Any ideas? Any conjecture?
It's got to be inducing a
Okay, it's got to be inducing a field. That's great observation or great analysis. It is indeed inducing a field. We have learned that if you have a changing magnetic flux, that it will induce a current, and that current will oppose the change. So if we look at this, I will draw some pictures. As always, if you want to play with it after class, you're free to. I love my toys. So we have a magnet, and let's say we have the north side down, the south side down. And it's going through this pipe. And so down below, what's happening to the flux as it comes down? Down below?
Well, it's spreading out, isn't it?
As it comes down, okay, as it comes down, you have these lines getting closer together because it's like you're moving. As this falls down, one place here goes from being like this, like this, like this. And so the lines are getting closer together as it falls. So the magnetic flux is getting stronger down below it as it falls. So below, the flux below is increasing. Well, Faraday's law of induction says that if I have a changing magnetic flux, it's going to induce a current. So I'm going to have a current that's going around the tube. And then we apply Lenz's law. Lenz's law says it's going to oppose the change in flux. So if the flux is getting stronger, then I'm going to induce a magnetic field due to that current that is going to oppose the change. It's going to go like that. So this is the induced magnetic field. Or magnet, right? But of course, north and north, what kind of force do we have between north and north pole? Repulsive. So I'm going to have a repulsive force down below. So that means I'm going to have a force that's pushing this up from below. Now, if I look at the top, what's happening to the magnetic flux as this falls above the magnet? It's decreasing. So the flux is decreasing. I'm getting current to make a magnetic field that's the same direction. So I'm going to have an induced magnet above that is going to, that was right. That is going to be pointing the same direction as the magnetic field because the magnetic fields go out of north. So there I have north facing south for my induced magnet above it, which is attractive, which is going to make a force like that. So the force top was pushing up. The force bottom was pushing up. Both of those forces are pushing up. Now the strength of those forces is going to depend on the strength of the induced magnetic field, which depends on the current, which is going to depend on how fast it's falling, how quickly the flux is changing. So as it falls faster, the upward force is going to increase. So what happens is it falls, and it will speed up until the opposing force is equal to the gravitational downward force, and then it falls at a steady speed. So it's kind of a brake to slow down the fall. But it's making current flow through here. That has a lot of useful ramifications. And I like to start with one that doesn't seem obvious. Roller coasters. One of the things that you really would not like to happen would be to be on a roller coaster and the power to go out and then you to just careen down and crash at the bottom. So I'm sure you've probably all at least seen, if not been on, one that takes you up and then drops you straight down. One of the scarier things was my sister and I were on the Malibu Screamer or something like that, I don't know, at Disneyland. My sister gets in, she tries to pull it down, doesn't get it to click. The lady comes by to check it. It's not locked. She just goes and walks by assuming it's locked. My sister's like, wait. She's like, oh, I would have caught it. Well, this one's broken. Go to another chair. That would be scary. It was scary, but we still stayed on there. I was straight to the upstairs heights. Okay, but that's not part of this lecture. You go up there, it holds you up there for just long enough for you to look down and get scared, and then it drops you. What's cool about this is you're essentially in free fall. You're essentially dropping with an acceleration of 9.8 meters per second squared. So we like to do things like put a nickel on our knee, and when you fall, you see it, because your knee jerks up a little bit, it comes up and just kind of hovers above your knee, right? Anyone done that? No?
That explains all the things on the Superman, right?
Okay, so what happens if you're falling down on that and the power goes out? If you look at the side of the tower, you'll see the side of the tower has these veins. And if you get near the bottom, they stick out further. And what they have is magnets that are on either side of that. And so when the vein goes between the magnet, it's going to create eddy currents in the vein. And those eddy currents are going to create forces like this to oppose the motion and make it slow down. So it has a built-in magnetic braking using what we just saw here. So that's a really practical use. What's another practical use? Anybody here have an electric vehicle? Nope. Me either. I've thought about it. Just saw something this week about those poor children in forced labor camps mining the stuff you need for your lithium-ion batteries for your electric car or for your iPhone. You can't pretend you're all holy because you don't have an electric car and then carry around your iPhone, right? Or your computer, right? We have lithium-ion batteries and everything. If you have an electric car, who's read up at least on electric guitars? Electric cars. Okay, we have a few people read up on electric cars. Where do they get the best the best economy? In the city. A normal gas car gets the poorest economy in the city. What's the difference? Okay. Speed, starting, stopping. When you're driving a car, you have to use energy because you have air resistance that's taking energy away. The faster you go, the bigger that is because the air resistance is proportional to the speed squared. So if you're driving at 25 miles per hour, the air resistance you have to overcome is far less than if you're driving at 80 miles an hour. Hence, if you had an electric motor, you should definitely be getting far better efficiency at the low speed than the high speed. Gasoline is a little different because you have different efficiencies for the engine, different RPMs, which of course is why you have transmission to begin with. But then you have another thing with the electric car, the braking. With a gasoline car, when you brake, you just scrubbed energy. It's gone forever. With the electric car, when you brake, you use this technology. Once again, we'll just call it a generator here, but it's still the same idea of when you hit the brake, you engage a generator that generates electricity, converting your mechanical energy, kinetic energy, back into electrical energy. So you accelerate, you use some of your electrical energy, you brake, you put it back into the batteries. And so when you're driving the city with an electric vehicle, you're constantly draining and then recharging the battery, and you have a smaller amount that you're losing to air resistance. So that's why it's reversed. I mean, the first time I saw it, I was like, they must have made a mistake. They must have written it wrong. We all know you get better fuel economy on the highway. But that's not the case for the electric vehicle because we're taking advantage of this. So here's some other examples. So here is number one, a pendulum that falls through a magnetic field. When I was in graduate school, we had a few demonstrations set out in the lobby of the physics building. This is one of them. You have a magnet, you drop it through a magnetic field. You have a piece of metal, a conductor. Drop through magnetic field. As the flux changes, it's going to create eddy currents. We call them eddy currents because they're going in circles like eddies. Yeah, whirlpools, eddies. So you have those currents going in a circle, and those currents going in a circle then are going to make magnetic fields opposing the change, and it slows it down. So you drop it in, and it goes. But then you can put one that is made out of a conductor but has slices in it. Why would the slices be different?
Because it can't conduct through the gaps.
Right, it can't conduct through the gaps. So now you're limited to only really tiny current loops. You still can have some current loops here, but they're tiny. So that means that the result is going to be much smaller resistive force. And if you put something that was an insulator, nothing happens. It just goes like normal. Now, I have to bring out my favorite demonstration. I can't believe I forgot to bring this out before class. Have I shown you my ring tosser? No. Okay, good. This is my favorite.
My ring tosser.
Of course, I have lots of demonstrations I like. It's one of those dangerous ones. Not as dangerous as the Jacob's ladder, but. And B, it illustrates some really cool things. So we start with power cable that I plug into the wall. That power cable is wired into a coil here. So if I put current through the coil, what's it going to do?
Create a magnetic field.
Create a magnetic field, right. And we have the equations now that we can calculate that. This here, besides being a reasonably good weapon in a brawl, is iron wires. Magnetically, what can you tell me about iron? It's ferromagnetic. That's what ferromagnetic means. It's magnetic like iron. So this is strongly magnetic. Now, something we didn't talk about when we talked about the solenoid. We talked about the magnetic field that's created in the solenoid. We said it's mu aught, the permeability of free space, multiplied by the current, multiplied by the number of loops, divided by the length. That's what I gave you for the strength of the magnetic field. But if I put this in, this is quite a bit more magnetizable than air. It's like 1,000 times more magnetizable than air. So when I put in this, I replace mu sub 0, the permeability of free space, with the mu for iron, which is like 1,000 times bigger, which means the magnetic field that this is going to create is 1,000 times stronger when I put this in. That's a cool thing. Then I have, and I'm going to limit myself just to these. Now, it would be nice if I just took my other one like this and sliced it. Then they would be identical except for one has a missing gouge. But no, I have this piece here. Now, all of these are not magnetic, the copper one included. But this one has cut out, this one doesn't. I'm going to start by putting a whole aluminum ring on there, and I'm going to plug it in. Now, what's the resistance in a wire? Roughly?
You pretend it doesn't exist.
Yeah, we pretend it doesn't exist, so roughly 0. It's not really 0. But if I plug this coil in to my power supply, I've done it with this before. That's a bad call, because then you just blow a fuse. It's a better call to just plug it in here, because if everything goes bad, it will throw a circuit breaker over there. So I'm going to plug this in. Now, when I plug it in, I got to plug it in for a short time, otherwise I do blow a circuit breaker because it's going to draw too much current. You got to love us physicists, right? We play fully safe. So I plug it in and observe what happens when I plug it in. What happened?
Moved.
It moved. It kind of rattled. Now, I told you this was my favorite demonstration. If that's all I'm going to do, it's a real lame favorite, I believe. Trying to move breakable things so they won't get broken. So now, what can I do to probably make this a little more fun?
Add the ferromagnet.
Okay, I heard add the ferromagnet, and that's exactly what I'm going to do. What did you say, Ryan?
Plug it in longer.
Plugging in longer just blows a circuit breaker. It doesn't make it more exciting, actually. So I'm going to put this in. It's going to make the magnet field like 1,000 times stronger. So if I have the magnetic field, now this is AC current. AC current means the magnetic field, the current is going one direction than the other. So the magnetic field is going up and down, then up and down, right? And that first surge is what's going to cause our reaction. Because that first surge is going to be 1,000 times stronger. So instead of just doing a little rattle, what do you suppose it's going to do? Okay, so we have to test it, right? We wouldn't be physicists if we just said, yeah, it's going to do that, and moved on. So it shot it up, right? Which is totally cool. Now what happens if I put this one on?
Shouldn't go as high.
Okay, shouldn't go as high. What were you saying, Ryan?
Oh, same as he did.
Same as he did?
Yeah.
Anybody else?
Shouldn't it just stay?
Okay, Trey says, shouldn't it just stay?
Yeah.
Okay, you changing your vote now?
I have no idea what it's going to do.
Well, we are scientists. We have to do this. Now, you might say, he just blew the fuse.
It didn't go as high.
You are absolutely right. That is not as high. Good call. I said I wasn't going to do it. I'll go ahead and put the copper one on. The copper ring is heavier, but it turns out fundamentally does the same thing. So what was going on here? What is the name for the phenomenon that was making this toss the rings? Eddy current. Because when I had a changing magnetic field, it induced a current which made an opposing magnetic field, opposing the change. If I had a constant magnetic field, what would happen? Nothing. Nothing, because you don't induce anything with a constant magnetic field. So if I take to a battery, the instant from zero current to a big current. So I would have something that occurs when I connect it. And then after that, it would be inert. It would just use a lot of current because it's a small resistance. All right, so I find this, it's physics. By now you figured out I find physics really exciting, right? This is one of the things that is totally fun. Now, inductance. We've learned Faraday's law of inductance. Inductance, when we use it in electric circuits, is talking about using Faraday's law of inductance. So what I have pictured up there is called a mutual inductor, which is another name for a transformer. So if you look at that picture, notice I have coil 1 and coil 2. An adjustable power supply. The adjustable power supply is funny. One of the fundamental rules for a transformer, which is what a mutual inductor is a transformer doesn't work with a battery. It doesn't work with a battery because you need to have a changing magnetic flux. And a battery is going to create a constant magnetic flux. So I would have really preferred if they showed this with an AC source. So let me fix it. You put a circle with a little tilde in it. That means an AC source. A little tilde, sine wave. That means an AC source. Now it's going to work for me. So if we look at this, I have a coil here. N1 is going to be the number of loops in coil 1. N2 will be the number of loops in coil 2. And I have I1 going through coil 1 and I2 going through coil 2. Now coil 2 doesn't have a power supply. How this works is, if I have current 1 going through loop 1, then I'm going to have flux is equal to, remember the equation for the magnetic flux? It was the number of loops times the magnetic field times the area. I just put A because we have the same area for both of them. I just put flux, phi, because I have both loops around the same magnetic core. This here, because it makes the magnet feel like 1,000 times stronger, it's basically going to keep the magnetic field lines uniform through here, so the magnetic field here should be the same as the magnetic field here. Or in this picture, the magnetic field where coil 1 is should be the same as the magnetic field where coil 2 is. So that's why I just put phi, even though I put B1. But B1 is going to be the magnetic field created by my coil. So that's going to be mu. I'm not putting mu sub 0 because I have a core that's not air. If it's air, it would be mu sub 0. Multiplied by current 1 over, and multiplied by N1 over length 1. The length of that first loop. So that's the magnetic field that's created, and then the induced EMF in coil 2 is equal to minus N2 change in flux over change in time. Well, the number of turns and the length aren't going to be changing with time. Neither is mu, my permeability. So this comes out to be minus mu N1, N2 over L1. Oh, I forgot area. Area. Change in current 1 over change in time. So the induced voltage in the second coil is related to the number of turns in the first coil times the number of turns in the second coil times the area of my loops divided by the length of the first coil and then the rate at which current is changing. So that's how we induce a voltage with a transformer. Now, in an ideal transformer, power in equals power out. And so power is equal to IV. So you should have ideally that I1 V1 equals I2 V2. This is ideal. You know what real is? Non-ideal. Why is it non-ideal? Well, let's go back to what's going on with this right here. How does this make the magnetic field 1,000 times stronger?
It takes up the space of the air.
Well, yes, but it has to do something the air didn't do. It's not conduction in this case. It goes to how is a permanent magnet made? Remember we talked about magnetic domains, regions that behave like little bar magnets? When I put this in a magnetic field, those little domains rotate so they align with the magnetic field. And that's what makes the magnetic field so strong, because suddenly this becomes a strong magnet. But of course, if I take these little domains and I rotate them, that required me to apply a torque for a certain angle rotation. That's work. So there was work required to make this become magnetic. And then if I reverse it, there's going to be work required to reverse the magnetic direction. So there's energy that's taken up to make it change its magnetic orientations and make it strong magnets. So that means you do have some power loss. The only way to avoid that is to somehow get perfect coupling, that is to make sure that your magnetic field going through one is exactly the same as the magnetic field through the other with no loss, and have air. So you call that an air coil transformer, but then you have some efficiency issues, so, because of the coupling. But a signal transformer, if you ever see the term signal transformer, those are transformers that are made that should be pretty close to this ideal behavior. Now, I didn't do all of the math here to give us the relationship, but it turns out that the ratio of the voltage into the voltage out should equal the ratio of the number of turns on the input side to the number of turns on the output side if you're in the situation where a transformer works. What was the situation where a transformer works? It must be a specific kind of current. Alternating current. If you have alternating current, that equation is true. And then if it's ideal, then the rest of it's true as well. So that we will be working with ideal. Don't worry about real. Just worry about the ideal. And so the point of a transformer here, why we use it, is twofold. Number one is it allows us to shift voltages. If I go from here to Great Britain, they use twice the voltage of what we use coming out of the wall. And so if I use a transformer, I can use a transformer that has the ratio of the turns set so that it will cut the voltage in half. So what should that ratio be if I want to cut them in half? If I want V1 to be 1/2 of V2, so V1 over V2 is 1/2, what should I have for N1 over N2?
1/2.
1/2 as well, right. So I can set my coil ratio to allow me to step the voltage down or up as necessary. So that's one of the key reasons to use a transformer. Another one is isolation. The first circuit, the one called the primary, that's the input side, is not in any way electrically connected to the output side, the secondary circuit. Right? There's no wire connecting the two, which means the reference point for the input side does not have to be the same as the reference point for the output side. So it allows me to shift my reference points. So that isolation is the second reason that we use transformers. Because you might wonder, why would you want a transformer that's one-to-one? Because it allows me to isolate and not have to worry about a ground that I had here. I can make ground here something different. Now, a few questions about transformers. What is the output voltage of a transformer with N1 is equal to 100, N2 is equal to 200, and V1 is 12 volts DC? Okay, 0. I'm so glad you came up with that. This question, I have put it on tests, and it's one that is missed way more than it should be because people don't think about the physics involved and just think about, oh, this is the equation. But you have to have AC. If it's DC, you don't have any output because you don't have any changing magnetic flux. Transformers require that changing magnetic flux. So now, let's repeat the question, but make it AC. So remember the equation. Notice the I's have the indices reversed versus the other two. That's so V1 I1 equals V2 I2. So if I have V1 is 12 volts, N1 is 100, N2 is 200, what am I going to get from my output?
6.
Okay, I'm going to actually solve it rather than saying yay or nay. So I have V1 over V2 equals N1 over N2. Therefore, V2 is equal to V1 N2 over N1 is equal to 12 volts times 200 over 100. So it's 24 volts. What's wrong with my answers? They all need to be, you're right. Well, you don't need to put A or D for a 0. But it's going to have an output that's also an alternating current, not a direct current. So that's how transformers work. Do you understand the principle of a transformer? Yes. The actual calculations you have to do with transformers are as simple as what we did here. You don't have to do the calculation like I went through here, relating the induced EMF to the rate at which the current changes. Except we have this equation. Well, actually, this is an example. Transformers and power delivery. In our electrical grid in this country, we have high voltage lines going across the country. Why high voltage lines? Yeah, I believe Mira's on the right path, but I couldn't hear the words that she actually said.
I can pretty much, you're going to lose voltage or current as you go. It just dissipates, so you need to keep it high voltage in order to travel long distances. That's my guess.
Okay. It has to do with energy loss. You're going to lose energy, and the power, the energy per time you lose, can be written as either I squared R or VI or V squared over R, right? Well, for a power transmission line, you have the current going through the wire and the resistance of the wire. So the easiest form to use for a power transmission line is I squared R. And so if I want to have minimal power loss, what do I need my current to be? I need it to be low to make P as small as possible. This is the power loss, right? So to have a low power loss, I need to have a low current. But I want to deliver a lot of energy, and so the power I'm delivering is going to be the voltage that that power line is at multiplied by the current. So I need a high VI, but I want a low I. So how do I give a low I with a high VI?
You just change the resistance.
Well, no, the resistance, we're going to use as low resistance as possible. But if I raise voltage, I'm going to have a smaller current because of the higher voltage. And because of that I squared term, if you go from 120 volts to 350,000 volts, what is your current going to do? It's 120 over 350,000 of what the current you're delivering to the household is. And then if we square that, because the power loss is proportional to the current squared, well, I'm just going to do that. 120 divided by 350,000. And then I square that. And I have 1, 2, 3, 4, 5, 6, 7. So the power loss is going to be about 1/10,000,000th as much by going up to 350,000 volts instead of keeping it at 120 volts for the long distance lines. So I think you can see there's a really good reason that we have high voltage lines. Of course, there's a downside. What would downside be? Dangerous. It's more dangerous. You have, like I talked about our family friend with the pipe and tilted up and the pipe hits that high power line, you don't live through that because the current that's going to go through your body is going to be pretty extreme. Okay, self-inductance. We're going to have to stop here at the self-inductance. An American scientist, there aren't that many of the American scientists that we study in a physics class because most of the stuff that we're looking at is pretty old. But Joseph Henry is the first one to wrap insulated wires around a core, which is basically what I have here, insulated wires wrapped around a core, and to work with that and look at the self-inductance. So we will, in lab tomorrow, actually, I believe, look at some self-inductance ideas. And the units are Henry's, named after Joseph Henry. So have a great day. I'll see you tomorrow.